the atomic theory. And the thing was that all of chemistry could be explained by assuming the existence of things called atoms, small indivisible particles that repelled each other when close together and attracted each other when far apart. And it explained why 2 volumes of hydrogen plus 1 volume of water, of oxygen, made 1 volume of water. Because if they were all made of these little indivisible particles, they'd combine in a certain ratio. But the hypothetical things called atoms were completely undetectable. There was no way to see if there's an atom or not that existed, until Einstein found out that the motion of pollen particles on water was exactly what you'd expect if atoms actually existed. So before Einstein in 1905, they had this theory, which was that atoms existed, but they had no way to show that atoms existed or not. It was just this hypothetical thing. And I say that now because that's where we are with this thing called string theory. So we now know a wide range of particles: protons, neutrons, electrons, mesons, neutrinos, muons, many more. And we know the forces of nature. And at the moment, we have a theory called the Standard Model that describes all of these and their relations to each other. But it's a complex thing. It's like the periodic table. There are hundreds of particles. And those particles, some of them, like the protons and neutrons, are made of quarks, 3 different kinds of quarks, red, green, and blue quarks. But still, there's a lot of them. So people started to look for a fundamental theory that explained all the particles and all the forces of nature. Like right now, we've got electricity, and then magnetism, and then Einstein showed that electricity and magnetism were really the same thing. You could use one equation to describe them both. And then there was another force called the weak nuclear force in the 1970s that was shown to be able to be written in the same equation with electricity and magnetism, so we call that the electroweak force. But there's also strong nuclear and gravity, and we cannot combine right now strong nuclear and gravity all together. So it would be nice to have one theory that put together all the forces and one theory that described all the particles. So mathematicians began to look for a way to write a theory that described everything we knew about it. And they found that if you added dimensions, instead of the 3 dimensions of space and 1 dimension of time that we have in our world now, that if you went to 10 dimensions or 11 dimensions in space plus time, then you could write equations for things that described all the particles and all the forces. And the problem was that this description has never been completed. In other words, it's not a complete description yet. It's just the basic idea has been shown to be possible, but they don't actually predict the result of any experiment that can be done. So they're somewhere they can describe everything that exists, but we can't prove them wrong. So it's in the same state that atomic theory was before 1900, where it predicted everything that was known. It actually even predicted new things, which we could look for and find. But you couldn't actually see the atoms. Well, string theory is actually slightly worse in condition right now, because it can be written to describe everything that exists, and many more things, but we cannot test for whether the things it predicts actually exist or not. There are no tests yet for string theory. So, and in fact, it's not, nobody uses it. Chemists actually used atomic theory before it was shown that atoms existed because it was really useful to explain chemistry. But nobody actually, no experimentalist actually uses any part of string theory to understand physics at the moment. So it's this tool without a use. And so mostly it's used by string theorists rather than by actual working scientists. So unless and until they actually manage to do an experiment and show that a prediction of string theory actually is true, or prove it wrong, it's just one of those theories. So it's not an experiment yet.
What do you think?
I'm an experimentalist.
Okay,
I think
you've
it's
got to be able
a
to-
lot of money being wasted on a bunch of theoreticians.
Got to show it.
So I'm an experimentalist. I'm glad someone's working on it, but I don't think we need 1,000 people working on it.
Okay. Were you going? Did you want to draw something?
No,
or?
that's right.
That was it. Okay. Okay. Well,
I did it with the atoms.
and you said there was some book that she could read.
Yes. So the best book on this is by Brian Greene, Greene, and it's called The Fabric of the Cosmos. And it tells all about string theory. And it's quite readable. It's actually written for a college-educated adult, not necessarily science-educated, but someone who can read and encounter good ideas. Oh, I'm sorry. The first book to read is The Elegant Universe by Brian Greene, and he builds up slowly through the history of science and ends with string theory. And then The Fabric of the Cosmos is another book that goes beyond that and tells you some more. But those are two great books to read. And he's the world's best string theorist, so he's really in favor of it.
Okay.
And I'm an experimentalist, and I think it's a lot of waste of money, but I'm glad someone's doing it.
Thank you, Paul.